All right, so now what we're going to do is visualize all that in EMTP. In this case here. Okay, so what do we do here? We have, it's a very simple case. We have this line here, which is 100 kilometers. And so we energize it. What happened here is that originally, so we have the line, we disconnect the line, and then we reconnect the line. So we have trap charge. You see that we cut the line in 3 sections. Okay, so we have we can visualize the voltage in between. Then you have other incoming line in the substation and network equivalent at the end. And here you have a resistive load. Okay, so then here to do all the analysis, I will use the switching toolbox, which is available for everyone. I mean, which is available. You can contact us, and we'll let you know how to get it. And so in this switching toolbox, you have some little meters. Those meters are used to probe and to give the characteristic of an equipment. Let's say you have a transformer. So you will bring this probe here, connected there. And then, so you first select what voltage you want to monitor during the statistical run. So here all phases. But then you see if it's a transformer, you select internal insulation, and you put here the BSL. It's pretty nice because you also have the standard. For example, here it's a 400 kV system. So if we go to the max voltage, here is 420 typically for the max RMS voltage. And it gives you automatically a typical BSL for this value. Same thing phase to phase. Here it's 400. Can give you that. Then so this is now for a transformer, an internal. So it means that when we run the simulation in EMTP, then in the processing it will be the deterministic method which will be used. So we determine the maximum, the truncature voltage, the maximum assumed maximum voltage. We'll compare that with the BSL, and that's how we'll determine either it's failure or not. Okay, the second way here is if you have an external insulator. In this case, same thing, you enter the BSL, the CFO, but here you will also need the height and the distance between conductor. Okay, so it's H and D. And by doing that, it helps to basically calculate the coefficient F1 and F2 that we discussed over here. Okay, so all these calculations will be done automatically if you enter these two values properly. You also have extra options because the calculation of B and of F1 and F2 also depend on other things, like if you have range 1, it put beta equal 1. If the radius is if it's like a GIS, so it does things like that as well. Okay, so that's the first step. You will place those little probes everywhere at each critical equipment where you want to assess, basically, where you want the process, the method to be applied. So here we do it at the substation. We basically gather all the BSL, BIL in the substation, and we took the lowest one at this point. We assume it's the same voltage everywhere in the substation. We put one at 2/3 of the line and one at the end. So here we assess phase to phase and phase to ground. We also have here an open switch at the end of the line, and here we assess what is called the longitudinal overvoltage. So when you have the circuit breaker open, so the contact aspirated, even if it's completely open, if you have a very high voltage, you may have a flashover between the two open poles. And so here, this is treated as a phase-to-phase overvoltage, and so you have a specific probe for that, which is the insulation coordination longitudinal voltage probe that you should place here across the switch. Okay, so the next step will be then to set up and run the statistical simulation. When this is over, you have this tool here, which is called Statistical Switching Analysis Result. And I can quickly go ahead on myself and show you what it does. So let's say you have run the 200 simulations, it will process all the results. And for each place, for example, let's go to line hand here, which is there. It will tell the maximum simulated voltage. So this is the maximum voltage reached during the simulation. What was the simulation run which got this? So when we do the statistical simulation, it's random. And maybe you are interested to run the worst case scenario. So here you have the number, the simulation number, which was this worst case. And actually, if you click on it and then click OK, you can run again this simulation. So if I click on OK, it will automatically run this run 100. Then you have the maximum statistical voltage, UT, which has several names, truncature voltage or truncature over voltage or maximum assumed over voltage. So this one is statistically calculated. You see that typically it's higher than this one, the first one, but it's not necessarily the case. You know, it's a statistical. So if you do many simulations, those two should be very close. But then if you don't do enough simulation, you may find things which are a bit surprising. Here we see that most of the time it's the case. I see here it's not, but still not so far. Then you have E2. So E2 is again the overvoltage which has 2% chance to be exceeded. So it's for phase-to-phase, it's calculated directly. For phase-to-ground, for phase-to-phase, you have two values. So you have the one from the meters which are placed phase A to phase B, and then you have the one which is adjusted using these equations. So that's why you have two columns here. So you see that when you have here a switch, for example, VA, VB, VC, it's phase to ground, so it's the same. But then if you look here, for example, so you have VBC, you see that E2 is there and E rep is here, and it's not exactly the same, which probably means that beta is not equal 1 at this place, and that's why it's not the same. Okay, so then it also automatically evaluates the failure rate. So you see here, for example, we have 40 failure per 10,000 switching, so it's pretty reliable. So it means it's basically one failure in 200 switching. So the job is completely done here. Now you have everything done, and what you can do is you may manually. So here the BSL, all these parameters are the same that you entered in those probes, and you may readjust them if you want to see the impact on the switching. For example, here if I put 1800, okay, so here actually it doesn't work because it should be lower than that, but let's put 1600. So it automatically evaluates the risk of failure, and so which is very nice. When you modify a value here, it will not modify the value there. This is just to try, but then if you select a value, you should do it here. If you want to also follow manually the IEEE procedure, you have here F1, F2 beta, which are shown here, the value used, so you may access that. All right, so now, so I show you how to basically process the result, but now I'm going to show you how to start the statistical run. Okay, so the first thing to do is, of course, to place the circuit breaker. So here we are going to do the statistical simulation for one configuration. Again, if you have different possible configuration where some more lines in, more lines out, you should repeat this process several times. You may automate that as well. Okay, so here we have this little node, which is a sub-circuit, and in there you see the different switch. You see two switches. One which is initially closed and which open at the beginning of the simulation. So this will create the trap charge. And then you have this one which closes after a little time. Here you see 13.38. Basically, as soon as you disconnect, nothing moves anymore. So you don't need to wait the real closing time of the circuit breaker. You can put any time here. As soon as the charge are trapped, they don't change, so you can close at any moment, basically. Here you understand that when you simulate this process, opening then reclosing, at the beginning of the simulation, whatever the closing time first, the closing time is the one which varies, so you will change the closing time, but the beginning of the simulation is always the same. You disconnect and then you reclose. So all the 200 simulations, the beginning is the same. In EMTP, there is a special feature where the software will see that the beginning is always the same for everyone and run this part of the simulation only once. Then all the other simulations will be started after this point which was selected by the software. This point is called the time of dice roll. It's automatically determined by the software. But it's nice because it means you may simulate a pretty long disconnecting event. For example, here you may disconnect the line. Let's say you have something which has a slow dynamic. You may wait 1 second, 2 seconds, and then do your statistical study. This first second will not be rerun all the time. So it's a huge gain, a huge time saver. Okay, so how do we do that? So let me basically put this switch here on the side and show you what to do when you start from 0. So the first thing is you will bring here an ideal switch. Select one to the mean time of closing, so just to have a value. So we can put here 20 milliseconds. Okay, so here the 13.38 was kind of determined to get a bad overvoltage. So it's after doing the study we found that was a pretty bad case, but at first you don't know. So when you open after like quarter of a cycle, all the or half a cycle, all the phase are disconnected, and you have those trap charge. So here we decide to close at 20 milliseconds to leave time. And so here what we will have to do is to work on the random data. To enable the random data tab, you have to place here this box. Okay, if you don't have this box, and if I bring an ideal voltage source, I go to random data, see I have this option is only available for random data in switch in statistical kit. So what you have to do is bring this device. Where do you find it? You go to option and statistical option. Okay, so you have to go there and you have to enable here statistical. Okay, we'll get back to this device, but first to set up all that, but let's first finish with the breaker. So now we have this device. If we go there and we go to the switch, we have random data, and now we can select things. So that's where here you will determine the characteristic of your breaker, the precision of the breaker. So that's where we determine those Gaussian distribution, which will determine the difference in closing time. So when you have the three phase closing, the three phase, I repeat, do not touch exactly in the same time. There will be a dispersion, and that's where you will find this. That's why you will specify this. Okay, so the first one here for phase A, you select Gaussian. You put here the mean time. So which is the same as before, 20 milliseconds. So the mean time here is 20 milliseconds, but it will be very linearly over a cycle. So a number between 0 and 1 cycle will be added to that, common to the three phase. We will do that in later on. I will show you how. Then you have the standard deviation. Typically for an SF6, it will be the 15 milliseconds. It may vary from different breaker technology. Okay, so that's pretty much it. You do the same thing for each phase. Okay, and you're done with setting up the random data. Just quickly, here you see that you have a dependency. So what is that? This is for the case of pre-insertion resistances. When you have a pre-insertion resistance, you don't have only one switch event, you have two. First, you close the pre-insertion resistance, and then after a certain period, you close the second one. And the second one has a constant timing as a constant timer after the first one. And so basically you will have a master, which is the first one to close. So here the pre-insertion resistance. And then you have a slave. And when you select a slave, here instead of having mean, you will have a mean of delay. And so you will put here the delay, typically 8 milliseconds, between the master, the pre-insertion resistance breaker, and the slave. And you will have here to put the name. So let's say, for example, this one is called SW2. You will have here to put SW2 and then the phase A. Often you will put all of them to phase. The reference will always be phase A. It depends how the mechanism is done for how the mechanism is built. All right, so that's it here. So the last thing to do here is to go in the scope tab and select here random switching time. So this, what it does, it will tell the software to save for each run, to save those random switching time that were determined. So the software will run simulations, find a Gaussian number for each phase, add up common delay between 0 and 1 cycle, and those three numbers will be saved here as random switch times. It's important to have that if we want to rerun then the worst case scenario. So you have to select that for all switches which participate to the statistical. Okay, so at this point we are, I think, pretty much the same as this one, so we can just we can delete this one. Okay, so the switch is set up. So now what we have to set up is again the statistical option device. So far the only thing we've done is to select statistical. Then here I explain the time of dice roll in order to skip the initialization and to start each run only when there is a statistical variation and we don't rerun the beginning of the simulation. Now what you have to determine is the number of simulations. So minimum to get a good statistical result will be 200. Here, because we are live, and I mean we are doing a video and I don't spend too much time, I will put only 100, but for studies, put 200 or even 500. The more you do, the better. You have many options in there, which do not apply for installation coordination, but basically you can also define some steps instead of throwing out random numbers and doing a, how do we call that, doing basically using Gaussian and linear distribution, you may just put a step of closing time for each pole and do all the combination possible. So then you may find a worst case scenario like that systematically. So you can do that. It's not what is recommended. I mean, if you do that, then you cannot follow the IEEE standard, the IEEE and IC standard for IC and for installation coordination, and so you cannot use all these tools. But sometimes it helps for very specific case. For example, identifying a certain voltage. Here, the maximum multiple of standard deviation, what it is, it's statistical. So it means that when you have your Gaussian distribution, you may get a number which is very far away from the mean. And so basically, you have phase A closing at 20 milliseconds, phase B closing at 21, and phase C closing at 26, which at the end of the day does not make so much sense because still the three phase close at the same time. So here we just put a boundary, and if the switching time is 4 standard deviation away from the mean, we throw another number basically. We determine another number and run the simulation with this one. Okay, so that's the goal of this maximum of standard deviation. We actually use this value to find the time of dice roll. So when you enter that, you will use the time, will determine the time of dice roll with that, and you can enforce if you want to find a new number when it's the case. So it's a good idea to have that. All right, and so then here we do the statistical study for a closing breaker, and that's where here you will determine if you want your closing time to be vary over half a cycle or a full cycle. Here, let's do a full cycle. Typically, when everything is symmetrical, so which means you have the positive and negative voltage are symmetrical, you can do on half a cycle. Here we do a trap charge, which means when we disconnect, we are unsymmetrical because you don't have the same charge traps on each phase. So in this case, you have to do it on a full cycle, so 360 degrees. Okay, so then you have here you can scope if you want this delay. It's not used, we don't need it here for the procedure, but it's pretty much up to you. For output, to save memory, because when you run many cases like that, all the data points may be pretty heavy to store on the computer. So usually we save only min and max. However, you're free to save all simulations if you want. You can also restrict the interval where you want to find the min and max. For example, if before doing the switching, you have something else to simulate that may create overvoltages, maybe you don't want to visualize that, so it's something you can do. If you put 0, 0, basically there is no restriction. Okay, so that's now finished. Everything is set up, so we can run the simulation. So we see that now we have our statistical run starting. So we've done 2, 3, 4 simulations. You see that between each simulation, we start at approximately 30%. So which means this is because of the time of dice roll. And so now we just let the simulation go. All right, so now the simulation is completed. To watch all these overvoltages, here first of all, you have to bring this little device here. So it's from options and plot, and then double click on it. By default, so the base case will be selected. So here you have to uncheck that and select statistical simulation data and press OK. Then wait just a few seconds and mplot will open. Sometimes it may take a while, so be patient. Okay, so now it's organized pretty much like scope view, except that now you have min and max. For example, Vn is node voltage, and you have min and max. Here, be careful because when you have it's an AC system, so you may have an overvoltage which has a negative value. In this case, mathematically it's a min, but in absolute value it's a max. So you have to process min and max the same way. Okay, so for example here, if I look at phase A, and I here select that and plot that, okay, you see I have my case number and here the voltage. So that's the voltage for each case. Okay, that's case 15, 16. Okay, the line in between, that doesn't mean nothing. Okay, so let's say I'm interested in all of the maximum voltage for phase A, so min max. Here I can select that and click directly on min max, and then click on max bar. With the max bar, I would have the maximum for each case, for the phase. So min and max put together. So basically, we'll take the max absolute value of min and max, and for the first case number 1, this is the value, case number 2, etc. Now, if you do abs bar, you have the two of them, but separately. Now, for 2 cases, you have the minimum and the maximum. All right, now let's say you bring all the 3 phases. Okay, so if you do now the max bar, now you are in what we called the case pick method. Before I was doing the phase pick method, now I'm doing the case pick method. And you see that for each simulation, I have only 1 overvoltages. Okay, whereas before I had that for 1 phase, and 3 phase would have done 3 voltage. So all that, remember, the tool is processing all that for you. In fact, maybe I went a bit fast for that, but here when you look at, for example, the voltage in the substation, you have phase A, B, and C, and then 3 phase. So 3 phase will be the case pick method, and phase A, B, and C will be independently phase A, B, and C. Okay, so you have now the case-pick method. So let's keep watching what else we can do here. Actually, no, let me bring back those phases. Okay, the min-max on each phase. Then you have something called the the cumulative distribution function. So this is very important because you see it's giving you first the mean, the most importantly the max, so the max over all cases. But it also now returns all the statistical indicators you need for your installation coordination. The mean, the median. So the mean here we see 50% of the case. It's so actually maybe I can explain what it is here. Here you have the overvoltage and here you have the probability. So one mean you have 100% chance to have an overvoltage lower than that. Okay, 0 mean you have all chance, 100% chance to have higher than that, of course. Then 50 mean you have 50% chance to have higher or lower. And if I go to the 2% chance, it will be over here, so 98. So the value which is here will be my E2. 2% of chance to have higher, 98% chance to have lower. Okay, so the mean here it's at 50%. The mean, sorry, here is the mean is here 70, so the median it's at 50% here. And then you have the standard deviation, which is also calculated. All right, so now let's say I want to rerun the worst case, any case. For example, let's say I want to run this one here. So case number 20. So the way I do that, I will go to tstat and select all the switching time. So that's where you have to make sure you don't forget one. Here we have only one switch that produces the statistical simulation, but let's say you have a pre-insertion resistance. Here you will have to have the 3 switching time of the pre-insertion resistance breaker as well. So you select those. Okay, here I want case 20. So you will go, here and go to File, Save Random Data for Devices. Then select where to save this the file. Okay, let's call it switching times. Then here you have to enter now the run number, so it was run number 20. And that's it. So then you bring the device like I explained, the fixed random data. You open it, you disable, you uncheck disable, and you go select here this file that we just created, switching time, and press OK. Now if you run the simulation again, the statistical run will not start, and instead you run one single simulation which corresponds to this case. Okay, and so similarly, if you use this device here, it will be the same thing. So now it's the first time I run it, so it will do the processing, which will take 1 or 2 minutes. Let's see if it's fast enough. All right, and so now very same thing. If I want to, for example, see the worst case associated with at this station here, I select 29 and click OK, and now it's running the same case here, the case number 29. And of course, we can visualize the results. So click on View Scope with Scope View and go visualize. Here. Okay, the voltage on the substation. Okay, so you see we disconnect with the trap charge, then we reconnect. All right, so that's it for the switching part of installation coordination. I hope it was useful for you and clear. Again, if you don't have this statistical switching result analysis tool, contact us and we'll be able to help you with that. Next video will be on the lightning transients and how to do insolation coordination for lightning. Thanks for watching and have a good day. Bye.